Okay, so what we're going to do today is continue our discussion from last time, and we are going to practice a little bit the topics that are related to the integral theorems, and we will also look at some of the divergence theorems and the transformation properties of vectors. That's a crucial topic. Some of you already know this from the ENM class, but it's important to kind of keep track of things otherwise anyway. So let's get started on this. This looks a little tricky for me. Give me just a second. I'm trying to get the okay, let's see. Yeah, I'm having trouble seeing you at the same time as the lecture notes stuff, but that's okay. I think I can switch back and forth. That's what we will do. So let's get started on this. So we talked about the integral theorems just very briefly last time. So let's take a look at the first one, which is the divergence theorem. Which relates the divergence of a vector field, so divergence of F, let's say, inside a certain enclosed volume. The volume is enclosed. So that's
you didn't share the screen.
Oh, okay. Sorry.
Sorry.
Give me just a second to show up. Okay, there we go. So all that we are doing is looking at the divergence of a vector field in an enclosed volume of, let's say, V, and that can be thought of as just the projection of the field on the normal vector to that surface boundary, right? So the normal vector part is crucial. So there's ds, which is a surface element. It has some magnitude, let's say ds, and the direction is n hat, which is normal to the surface. So at this point, for example, the normal would be over there if the volume of interest is this one, right? So the normal vector always points away from the volume. That's the convention we follow in ENM all the time. So make sure you understand that. And of course, divergence theorem can be used for a variety of very simple problems. Let's say you have a sheet of charge, right? So then let's see, there is a charge density sigma on the sheet. And you want to try to find out the electric field above and below, then you can use the divergence theorem with the help of something called a Gaussian surface. So you have to choose a Gaussian surface that encloses a small, or rather, actually, it's a Gaussian volume. So you create a shape that's going to enclose a certain amount of charge on the charge distribution that's been given to you. You have to somehow follow the symmetry of the charge distribution. And so for a sheet of charge, for example, the surface is called the Gaussian pillbox.
Dr. Kapale?
Yes.
Are you writing something?
Can you not see it?
Yes.
Okay, let's see what's going on. Let me stop sharing and share it again. I don't know why that happens. Okay, how about now?
Yes.
Okay. Now, do you see it still? I don't. Okay, there it is. Yeah, so I don't know what I'm looking at, but I can look at my iPad here. Okay, very good. So that's called the Gaussian pillbox. And so let's use it. Let's actually use this, apply this to the situation here. So what are your first thing we want to think about is what would be the direction of the electric field. So this is now, the sheet is infinite in extent. Okay. That's what I imply by these arrows that I just drew. So if the sheet is infinite in extent, what do you think will be the direction of the electric field?
Perpendicular to the.
It will be perpendicular to the normal vector, right? So above the sheet, it may be upwards, and below the sheet, it may be downwards, or other way around, right? It can be inward above the sheet and inward below the sheet. So it could be directed away from the sheet or coming towards the sheet. Both are fine. So I should, strictly speaking, it should be plus or minus, right? Both are okay. That's because of just the symmetry of the situation. Because the X and Y extent, let's say the sheet is in the XY plane, the XY extent is infinite. That means the electric field cannot be a function of X and Y, right? It has to be a function of only the Z coordinate. Okay, that's how it should look like always, right? Everybody with me? That's just because, coordinate goes from 0 to infinity. You want the field to be physically meaningful, so you can't have a X and Y dependence. That's all there is to it. So these kinds of arguments are very, very common in ENM. So you kind of have to develop your idea for this. And we're going to now take the electric field to be very close. We want it to be very close to the surface. So we eventually are going to take the height of the Gaussian pillbox to be negligibly small. So which areas would you have electric field? So let's think about the surface integral of the ds started with E. How would you evaluate that, right? Let's say we're replacing that F with E. How would you do something like that? Any thoughts? So it would have, of course, different components, right? So let's just say the top lid E dotted with ds. For the dot product, I can change the order. That's not. Then the bottom lid, we have to separate the, and then what else? The curved surface. And we take this to be negligibly small, right? Because we're taking the height to be very small. So we're going to ignore that part. So you just have to find the electric field due to the top lid and the bottom lid. Let's take the charge to be positive. So the electric field is directed away from the sheet. So above the sheet, it's going up. Below the sheet, it's going down. And so both the integrals would be positive. Again, all that you would need is whatever is the surface area. Let's call it I'm going to use a little label here. The surface area to be A, let's say. Right. So in that case, what would be the electric field on that whole top lid is going to have the same value, and also on the bottom lid. So it can come out of the integral sign, right? And so you're just going to get EA plus EA, right? So it's essentially 2 times EA, right? And then the volume integral, which is the d cube R divergence of E over that volume, the whole volume, it essentially, I'm just going to directly give you because we can use the Maxwell's relation. And so this is just going to be sigma times A, right? A is the surface area and the charge that's enclosed. So this Gaussian pillbox is cutting through the surface sheet. And if you look at its projection on the sheet, that projection would have the area A, right? So this volume integral is just given by the charge density times A. It's essentially the total charge enclosed in the volume chosen. Okay, everybody with me? I'm assuming, of course, that you know the one of the Maxwell's relation, which is divergence of E equal to rho over epsilon. In this case, rho doesn't appear, right? Because you don't have a volume charge density, you have a surface charge density. We will see later on how to deal with a situation like that in a minute. Okay, but that's the so then you get sigma dot A is going to be 2E times A. So the electric field is sigma over, actually, there is also epsilon 0 here, right? So I forgot the dimensionality. Should be 1 over epsilon 0 times this. So you get sigma over 2 epsilon 0, and the direction is n hat. So the electric field is up. Above the surface, it's positive. Below the surface, it's negative. But it's always in the direction n hat. Everybody with me so far? Does that make sense? Okay. Then with this, you could take an extension of this. And let's say if I gave you 2 sheets of charge, and one has the charge density, let's say positive sigma, the other one has negative sigma, you can then calculate the field between those 2 sheets and outside, right, above the first one and below the second one. And then that's something to think about. In this case, you don't have to do 2 Gaussian pillboxes and do everything again. There's no need, right? Because you know the electric field due to one sheet, so you can map it out. Because of one sheet, the electric field due to the second sheet would have opposite sign, and so you can map it out and then add it all together and see that it's see the total value. One thing that's interesting here is that it does not even have no z dependence, right? So no, it does not even depend on z. It does not depend on how far you are from this infinite sheet of charge, because the farther and farther you are, larger and larger amount of the charge on the sheet has influence on that position. And so, it doesn't matter how far you are from this infinite charge sheet, you still have no z dependence. Okay, so that's the okay. Do you still see the written page, or you don't see that now?
You see it.
Still
You see
see
it.
it.
Okay, that's good. I wanted to make sure because I changed something on my screen. Okay, so that's the divergence theorem, and we kind of also saw the application of that. There are a couple of special cases that are of interest. So let's take a look at some special cases. And one of them is the vector field that you're talking about is actually just some constant
Dr.
field.
Kapale,
Yes,
it's not working again.
it's not working again. Okay, so I think there is something weird about it. I need to find out a way to fix this. Give me just a second. Give me a second to see what's going on. If I can fix it quickly, I don't think I don't want to spend too much time on it though. So what we're going to do, let me see if I can move Zoom to a different screen. Does that work now or still an issue?
Last thing you wrote special cases.
Okay, so what I'm going to do now is try sharing it again. I'm trying to change something here. No, it keeps flipping back and forth, which is what's causing this. Okay, how about now? I think it will be better now. I figured out a way to take care of this. Can you see it now?
Yes.
Okay, very good. So we're in business. So let's now take a look at the special cases. So the special case is the field composed of two parts. The vector part is constant, and then you have a scalar field part. The scalar field is a function of r, which is vector, but that is the specially dependent part, right? Because c is a constant vector. Derivatives of it are not going to appear in the relations, and so what we and you can then form another combination for the function through a vector product of a vector field and a constant vector c. Okay, so both of these can be thought of as useful, and in that case the divergence theorem takes a slightly different form. So the divergence now becomes the volume integral part. The divergence of f is going to become just the gradient of the psi function, right? Because the you can't apply divergence to a scalar field. You can only apply it to a vector field, and so it gets transformed into a gradient. And then on the other side, you're just going to have basically ds multiplied by psi. C gets canceled from both the sides. You essentially get C dotted with on both the sides, and then you can get rid of it. So that's what that happens. You know, it's something you can quickly prove, nothing complicated. For the second case of the cross product situation, you get curl of the vector field inside of the divergence instead of the divergence, and the other side, because now this is a vector quantity that's being integrated, you should have a vector quantity that's being integrated on the other side as well, and so you get a cross product between ds and a. And these things you can very easily prove. Take the original divergence theorem, substitute the special forms of f, and then you can prove these things. So they're very straightforward, nothing new there. Let's take a look at Stokes theorem and its special cases. So Stokes theorem, of course, is the surface integral of certain surface here, and then you're trying to do a surface integral of the curl. So I'm showing kind of graphically. It's not a letter G that I'm writing. I'm showing a curl, with arrow. And so if you do a surface integral of this quantity, curl of f summed over, when you do integral, that means you're summing it over the whole surface, and that is going to give you the line integral of the function. So you can basically add it all together, and that gets converted into a larger line integral that is just on the boundary, right? So geometrically, you can sort of see it makes sense. Here also, you can apply the special cases, constant vector multiplied by a scalar field, or f is replaced by a cross product of a and c, where c is a constant vector. Then you get the relation turned around a little bit, and it becomes the volume in the surface integral becomes now a cross product between ds and gradient of psi. And on the other side, you just have dl psi. Or in the second case, it turns out to be dl crossed with a equals dsk gradient of ak. So this one now gets a little complicated. I'm just writing it the other way around to make it simple. So the contour part is simple, but the surface part has two terms in it. Okay, and then that looks complicated enough that we are actually going to try to prove it. Okay, so let's prove this second relation. So let's take the standard left-hand side of the Stokes theorem. Okay, so that's what we're going to do. And what we get is the surface integral dotted with curl of f. Okay, and f we are going to take, of course, as a crossed with, sorry. Okay, so then when we substitute, we are going to get ds dotted with curl of a cross c. And you know how to simplify the double cross product using the Levi-Civita symbol. So I'm going to skip a few steps here and directly write down what this is going to look like. It's going to have a, so sort of like the back cab rule, but there are more terms in this case because you have a derivative operator which is going to apply on both a and c, right? Now, eventually two of them will cancel, but we have to write down all of them. So this is like a back cab, right? P, AC, right? And then C, AB. So that's that. But you're also going to have a couple other terms because it's a derivative operator, not just simply. And the other terms are going to be C dotted with the gradient applied to A minus A dotted with the gradient applied to C. And you can convince yourself that this is the case because of the derivative operator. So, due to this symbol, if you take a look at its I component, you're going to have two Levi-Civita symbols. They're going to get converted into two terms with products of deltas. but because you have a derivative operator on the right hand side, even though it seems like because of the delta combination you have only two terms, but the derivative applies on the two. So if you do the chain rule, you get two terms from the derivative, and so 2 times 2 you get total 4 terms. That's how this works. So you can you can convince yourself that this is true by trying it out yourself, right? And so if you look at the divergence of C, that's going to be 0 because C is given to be a constant vector, and also the term where you have A multiplied by the gradient operator applied to C. Again, it's now a derivative operating on C. C is a constant vector, so this is going to be 0. So these two terms vanish, and eventually you are only left with the two terms ds dotted with negative C times divergence of A plus A. Now A order doesn't matter, so we're just going to write down C. Oh no, it's actually in that correct order. C dotted with the gradient and multiplied by A. So which term survive? This term is equal to 0, and that term is equal to 0. So you only have this term survive and that term survive. And that's all that I have done. I've just collected those two and written them down. And now we're going to simplify these as C outside dotted with sum over S, ds dotted with divergence of A. It is going to be essentially ds k gradient AK minus C dotted with, sorry, I think I'm writing this term down here first, right? It's C dotted with, so C dotted is taken out. Then you have ds, but ds is dotted with the gradient operator applied to AK. So let's actually take some time and simplify this, right? If I jump directly, it's going to be a little tricky to explain. So let's take a look at the form of this term. If you want to help me, you can feel free to help me. So this is how this is going to look like. It's going to look like C dotted with, any thoughts anybody has? This is a vector, right? So you can, let's actually write down the whole thing. ds dotted with this whole stuff, okay? And let's write it down as the x hat component, right? Y hat, z hat, and then we will, afterwards, we will simplify this. So the x hat component of this is going to be C I delta I applied to AX. Okay, everybody with me? Ci delta I assume the Einstein summation convention, because C dot delta is actually a scalar and it would have 3 terms. It would have C1 or Cx delta and del x, Cy del y, and Cz del c, right? And then the y hat term is going to be Ci del I, Einstein's summation convention, do not forget. So that just helps us focus on the important term, not so much on the other term. Okay, now you're taking the dot products, and so what we are going to get is basically dsk, okay, times ci del I a k. Everybody with me? Because ds you can write, expand it out into 3 terms, and only the x terms will be a product of the x terms, product of the y terms, and so on. And so we can just then write this as Ci dsk del I okay, what I'm going to do is, yeah, okay, let's just write it down so that we can identify the dot product part correctly. Del AK I. So now I'm going to focus on these two. And you can identify the dot product hidden in between them. And so I can write down this basically as C dotted with TSK, the whole gradient operator applied to AK. Everybody with me? If you're not comfortable with what we are doing here, to help you understand this in detail, you can expand out everything in terms of the XYZ components and try it out, and you will see that eventually it comes to be like that. What does this term look like, right? So this is a vector, right? And so this is how it's going to look like. That means the summation is implied, right? So you have to sum over the K, but each component of A is now a scalar quantity. AK is a scalar, and that scalar, you are taking the gradient of that scalar and multiplying it by another component of SK, that is corresponding to that, and then you get this, right? So if you wanted to see how this would look like, it would look like C dotted with, let's say, DSX times gradient of AX plus DSY times gradient of AY plus DSC times gradient of AZ, right? So that's how this thing really looks like, right? It's because of Einstein summation convention, it has that compact form. Okay, so then the relation that we were looking at, so this first term which is actually the second term from this expression here, is what we just simplified. Okay, so only the gradient is the vector quantity, rest of those are scalars, and the other quantity, just the negative term, just stays as it is. There is nothing to be manipulated there, because the C is a constant vector. It comes out of the integral sign, and you're just left with this here. Okay, and then you can do the right hand side, which is the line integral or a contour integral over the boundary of the surface, is dl dotted with A cross C, and there also you could take the C outside. It's this thing can be easily interchanged, and you get C dotted with, because one of the vectors is a constant, you can write it down like that, and then you get the relation that we had. So we just proved this thing here. Remember, each one of those terms are being dotted with C vector, the constant vector from the left side. So we can get rid of all of those. And if you have C dotted with A equal to C dotted with B minus C dotted with some vector D, then you are going to, this is going to imply essentially that vector A is equal to vector B minus vector D, right? That's what we are using to be going from these two relations to the one that we had earlier. Everybody with me so far? Make sense? Okay, so let's see how many of you are there. Looks like not everybody came today to the class, is it? Let's see. Oh, maybe everybody is here. Okay, so what we're going to do now is a quiz time. So find a new sheet of paper on your notepad or whatever, and I'm going to write down the problems here for you, and you're going to work through them, and you have 10 minutes. So it's 8:38 now. You have 10 minutes, so 8:50 you have to submit. And I'm going to write the problems here now. Quiz 1. Evaluate A, which is epsilon I j k product epsilon I j k. Okay, and then the other quantity that you want to evaluate is a product of delta ij times epsilon ij k. Okay, so do not forget the Einstein summation convention. I j k run over the values 1, 2, 3, and I will give you this expression of I j k epsilon I L M to be delta JL delta KM minus delta JM delta KL. Okay, so you can use this. Okay, and that's good enough. I think you just need one problem. It's good enough. It has 2 parts already. So start working on it. I will create a folder on Western Online for you to submit. Okay, so your reading assignment before the next class is section 1.5.1. That's just delta function in one dimension, and you can see its different forms and the limiting structure. There is an example there.
Kapale,
Yes.
you write in chat or okay.
Are you seeing the screen? You should be able to see the screen.
In this screen, we didn't see anything new. We just see this one assignment in the.
Okay, let me see what's going on here. Okay, what I can do probably is stop share and share again. That way you will see it. Keeps moving out of the field of view. Okay, there it is. So that's the one that. Okay, sections 1.5.1, 1.5.2 you can skip. 1.5.3 is important, and then 1.5.4. And if there are any solved examples in between, you should be going over them as well. We will take a look at the 3D delta function in more, now we will use it, we will look at it more carefully and look at some applications of it. Okay, so that's your reading assignment, 1.5.1, 3, 4, and 5. And look at all the examples. There are at least 2 examples there that you can read through, and that should do it. Okay, so I'm going to let you go now.